The exam is going to be probably like a 9.97. Not, last year's was a 10. I went a little easy on you guys. Okay. Okay, welcome to class, everybody. I do want to point out I've struggled with my screen recording software. It will like record the whole thing, and then when it goes to finalize the video, it like times out, and I wait for hours and hours, and I can't seem to recover the video file. So the last lecture was not posted. I appreciate your patience as I work through these technical difficulties. So I'm trying some new software today that hopefully will be better. Anyway, we are now reviewing for your first exam, which is all going to be focused on conduction, which is going to be chapters 1 through 5. If you look at your syllabus actually points out which sections to exclude. So there are a couple of niche or specialty sections that I don't cover here. So if you're a person that likes to read the book, you can definitely read those sections if you want, but I won't test on those. I would recommend trying to solve problems and some combination of reading about the concepts in the book and solving problems. I try to keep the tests very focused on, do you understand the core concepts? Because I strongly feel that those concepts are going to be what stick with you long term and not memorization of equations. Okay, so we were joking around about how hard the exam was. So that's all relative. Last year's first exam, it was harder for students than I expected it to be. I did try to dial this one back quite a bit, but I do want to share this quote. This is one of my favorite quotes, and I think just a general guiding principle that you should all apply in your lives. So I have this hanging on my wall. I repeat this to my kids like at least once a week. That which we persist in doing becomes easier for us to do, not that the nature of the thing is changed, but that our ability to do is increased. So really a great principle about persistence. So dive in, study, solve problems, then those things will become much easier. So the exam, for example, may be easier for some because they've persisted, they've worked really hard at it, and then whether it's hard or easy becomes sort of relative to how much you've invested into it. Anyway, I just really like that quote. So and you need that in this program and in life. Things can be really hard. That shouldn't scare you away. You can do hard things. So just persist. Just keep chipping away at it. Even if you're not good at it, keep chipping away at it. You'll become good over time, but that'll be directly proportional to the amount of time that you've invested into it. Okay, so just to review the exam rules, it is a closed book exam. I will I'll have a printed copy of the equation sheet, so please don't bring your own copy of the equation sheet to use. You won't be able to. You'll have to use the one that I provide. In addition to that, you can bring 1 page of your own notes, front and back. So that 8.5 by 11 sheet at a maximum, so don't bring a giant poster. No one's ever tried to do that. Bring a calculator, absolutely no web-enabled devices. So no cell phones, laptops, smartwatches, anything like that. Just a calculator. Okay, any questions so far? So last week on Friday, I polled the class and just left it open to whatever topics you felt like you wanted to review, and those were sort of all over the map, but some common themes were fins. That was probably the most common thing, were fins. So we'll talk about fins today and review and solve a problem that has fins in it. Solving for temperature profiles from the heat equation. If you've gone back and been reviewing the old exams, I usually sneak a problem in there where you need to integrate the heat equation. And so your geometry might vary, your boundary conditions might vary. I try to have something that's not, you have to do the integration and come up with your equation that's not just a solution that you can find in a table. Transient systems, there were lots of questions about that. Using the lumped capacitance method and the one that has both transient things, so temperature changing with time and space. Thermal resistances, cylindrical and spherical systems, and then using differential energy balances. So I think that is a pretty good cross-section of everything we've covered so far. There are certainly some other topics that we won't get to. I mean, it's hard to review everything in a single hour that we've been covering for the last 6 weeks. So no guarantees or promises. So today we're gonna spend doing a combination of reviewing concepts and solving problems. And in fact, we'll look at the problems first and then go back and think about the concepts that will help us solve that problem. So these are just example problems. They're by no means intended to be representative of everything that could potentially be on the exam. Okay, so as I was searching through problems that would be representative of those topics that everyone asked about, I found that last year's conduction exam was a pretty good example. It was a hard exam, but it covered quite a bit of these topics. So we're going to first look at the 2018 exam, problem number 1. Okay, so this was also a homework problem, right? So this was a homework problem, right? Yeah. Okay, yeah. So I'm an optimization. My research is optimization and efficiency, and so I frequently recycle old problems and stick them in the homework. Okay, so a microchip with a bottom surface temperature of 344 Kelvin uses an array of fins to enhance heat transfer. The fins are square in shape, are insulated on their lower end, and have the dimensions specified in the figure below. The system is at steady state. So assuming a constant convection coefficient for all surfaces and a thermal conductivity of K equals 30 watts per meter Kelvin, how much heat does the array dissipate in watts under the conditions shown? So let's just tackle A first. How would we go about calculating how much heat this thing dissipates? Let's first think, so what modes of heat transfer are happening here? So we have convection and conduction, great. So if we look at an individual fin, so these fins are designed to help enhance heat transfer from some other base surface. So here's our base. So that's going to be at a temperature T sub B. So we attach this fin on there. What's the point of the fin? It increases the surface area. That's great. So a perfect fin would increase the surface area. It would conduct heat perfectly throughout, and it would just be at a uniform temperature, the same temperature as the base. So that's what a perfectly 100% efficient fin would do. In reality, this fin, we have conduction heat transfer going this way, and then we have convective heat transfer going out. So the fin is losing heat and temperature the further out you go. So our real temperature profile ends up looking something like this. So it's losing heat the further out you go, and if it were an infinitely long fin, it would eventually just reach the ambient air temperature. So there was an equation in the book called the thin fin equation, which was based on a differential energy balance. I'm giving you way too much detail here. There's going to be a shortcut. So the fin equation was based on a differential energy balance of the fin, assuming temperature varies only in the x direction and not in the, whatever we want to call this. This is a square fin, so let's call this the y direction, and maybe the z direction is going in and out of the screen. So temperature is uniform in the transverse direction, but it's decreasing in the axial direction. Okay, so I hope this is refreshing your memory on thin fins. So the book actually went through solving that thin fin equation for a number of different scenarios. Those scenarios all had to do with what's happening at the tip. So there was a tip condition. So here we could just remember that the solution to that thin fin equation for different scenarios are given they're given in here. Let me go find this. Should I open this one? Okay. So here you can go look up in the table. This is the actual sheet that you'll be given. So here are these different conditions. So we have, you could have convection happening from the tip. It could be adiabatic or insulated. It could be at a fixed temperature, or it could be infinitely long. So what's our tip condition for this particular problem? So it's adiabatic. There is a specific reason I did that, because I'm asking you in this particular problem to get the total amount of heat dissipated by the entire array. So you would start by figuring out, assuming everything, each fin is uniform, you would figure out how much heat does one individual fin dissipate. And where would we find that? Where would we find how much heat an individual fin dissipates? It's like, okay, yeah, it's right there. So in this case, when we have an adiabatic tip condition, we can get our temperature distribution here, and we can get our fin heat rate here. These equations, so remembering the concept was that when you have a thin fin, you have something sticking out into space where temperature only varies in one dimension, but then it's losing heat by convection. Solving that differential equation leads us to this point. And I think we've developed a skill set where you guys could derive that equation and solve it, but on an exam, you'd probably want to know what the solution is. So that's where these solutions come from. So we specifically want to know what the fin heat transfer rate is. So that is this equation. And this is why I picked the adiabatic tip, even though I have no idea why you'd insulate the tip, because it gave us this simpler equation that made it a little less cumbersome on an exam. So our heat rate, Q, is equal to big M times the hyperbolic tangent of ML. So as you start studying, it seems like we're not really remembering this particularly well right now, you can find the definition of those things down here. So this becomes pretty much just plug and chug. So far, this is just a plug and chug problem, but you got to know where to go get these equations. Okay, so from here we would go and plug and chug. So for an individual fin, we would use that equation that Q is equal to M times hyperbolic tangent times ML. So you'd find the M and the L from that table, plug them in, and I'm going to skip all that in the interest of time. This is all available, though, in the solutions that I've provided. 2.79 watts. Okay, so is that our answer? Why not? Okay, so that's what one fin does, but this is an array of fins. So how would we calculate how much heat the entire array dissipates? It means, yeah, good point. We haven't quite gotten there yet. It means all the fins plus the remaining exposed base area. Okay, so how do we do that? This was let me just say before you freak out, I regret assigning this a problem on the exam. Still a perfectly fine problem, but I'm not going this complex. So but the concepts are still important. We're still doing this now because these concepts are still important. So this would be like the number of fins times the heat transfer rate for each fin. Then we would want to figure out how much the exposed base, how much heat is lost from the exposed base. So then we would have the area of the, I'll just call this exposed base times H times T base minus T infinity. So basically we're calculating what each individual fin, so each individual fin sticks out into space, and so it's exposed to convection, and you have this temperature variance. However, the exposed base area, which is everything in gray, is still just going to be at the base temperature. So that area of the exposed base would be, it'd be something like the width times the length minus the area, the cross-sectional area of the fins. Questions there? I don't want to dwell on too much of the nitty-gritty of this problem. So we had 49 fins in this problem, so we'd expect our answer to be 2.79 multiplied by 49 plus this extra little bit of heat that still gets out of the exposed base. So that Q array ends up being 164.2 watts. So I skipped a bunch of stuff in there. I'm hoping that the concept is sinking in, though, that you kind of visualize what a fin does and what the temperature profile looks like and how is heat escaping from the entire array. Okay, so the second part of this problem is, what is the effectiveness of the array? So this is an important concept. What does the effectiveness mean? Yeah, great, and it's actually in the problem. So the effectiveness of an array of fins is defined as the total amount of heat dissipated. So we get our total amount of heat, which was 164 watts, and then we need to figure out how much heat would be dissipated by a flat surface with no fin. So how would we figure that out? If we had no fins, how fast would this little area be losing heat? What rate law would we use? Yeah, so our effectiveness of the fin is this going to be this Q array, whatever I called that. Yeah, Q array divided by Q base if there were no fins. So Q base, so is this number going to be less than or equal to or greater than 1? It should be greater than 1, right? Or that, because we're increasing the surface area. So our Q base is going to be H A times the width. Well, sorry. A is the width times the length of the base times TB minus T infinity. So this ends up being 4.18. So basically, having this array means that we dissipate 4.18 times the amount of heat that we would have dissipated if there were no array there. So, does anyone remember what the efficiency means? That's another metric. What's the efficiency of the... Let's go back to just an individual fin. So we're done with this problem. Again, detailed numerical solutions are available on Canvas, but we're focusing on the concepts here. And they're not really that tricky of concepts. So if we wanted to look at the efficiency for a single fin, what is the efficiency of a single fin? How is that defined? So it's the energy that it actually dissipates divided by the energy that it would dissipate if the entire fin were all at uniform temperature, meaning that if the fin were a perfect conductor of heat, heat would be delivered really effectively throughout the fin, and then it would just be convecting. So this is typically going to be, H times the total surface area of the fin times our base temperature times T infinity. So again, the efficiency of a fin is the amount of heat it actually dissipates, which you could get from the solutions to the thin fin equation that were in that table, and we just got for an individual fin, divided by how much heat would actually be dissipated if the entire fin were at the base temperature. Questions there? Is anyone still confused? Yeah, Donovan?
Is that mu on the left?
That is eta.
Okay.
Yeah, sorry. Okay, so that's the fin efficiency. So that's going to be a number. Is that going to be greater than 1, less than 1, negative? Okay, it should be somewhere between 0 and 1, right? So this is like the maximum heat we could possibly dissipate. And this is how much of that heat do we actually dissipate, because our fin is not going to be a perfect conductor of heat. Okay, so then what is this other metric would be the effectiveness of a single fin. And I guess I probably should relabel this one. This was the effectiveness of an array. And this is the effectiveness of a single fin. So what's the effectiveness of a single fin? So that's how much heat the fin dissipates, which we already calculated from that equation, divided by how much heat would be dissipated by that same area if the fin weren't there. Yeah, Nimdo?
How come for the base area we're not like subtracting the space that each fin like takes up on the base? You know what I'm saying? Because like I guess if we're like incorporated into the Q fin, then we're double counting, no?
You're talking about for this above?
Yes.
Oh, yeah. So, okay, we're backing up a little bit here. So Nimdo asked in the calculating the Q of the base. This is the Q of the base if there were no fins. So why don't we subtract off the area of the fins? Because in this case we're calculating what if we didn't have an array at all, how much heat would be dissipated there. Yeah, Donovan?
For the efficiency of the fin in the denominator, that was how much heat would be dissipated if the whole fin was at TB.
Yeah.
Okay.
So this is going to be total surface area of the fin. So you would want to calculate all the surface area over each side, and then also the tip, unless it's an insulated tip, of course. Okay, so the effectiveness of a fin is how much heat the fin actually dissipates divided by how much heat would be dissipated if there were no fin by that same area. So this is actually going to be this would be the area of the exposed base. And then this is going to be TB minus T infinity. So this is saying how much heat the fin actually dissipates, and then this is how much heat would be dissipated if you just cut the fin off and looked at that, the remaining exposed base if the fin were gone. So that, I guess, would be the same as the cross-sectional area of the fin. Cross-sectional area. Okay, questions there on fins? So I'd encourage you to go back and read through these problems again and solve them again. If you still have questions, go back, solve them again, read about it in the book to get the concept down. So hopefully this is a good refresher for some of you. Okay, so we just covered fins. We talked about arrays of fins, the array effectiveness, and these weren't specifically asked in the problem, but we also talked about the fin efficiency and the fin effectiveness. The array efficiency we didn't get to, but let's move on. Okay, so this is problem 2 from last year's exam. Yeah, there are 3 old exams on conduction posted with the solutions. So these are all posted with the solutions. The solutions tend not to be super explanatory, so you may have to do a little bit of digging to find out why I did what I did when I came up with the solution. Okay, so this time, you know what, I'm going to give you 30 seconds to read through this problem. Just don't read part B. So I'm going to give you 30 seconds to read through it, and then maybe another 30 seconds to think about how you would approach it. And then I would like someone to raise their hand and tell me their thought process. How would you attack this problem? Yeah.
Just in the previous problem before, I saw like there was a H is equal to 40, and then the problem statement that said 150, and I was just wondering why there was 2.
Oh, yeah, there was a typo, yeah. We got that resolved last year. Okay. Who feels like they have a thought process to work through this problem? James? Okay. Okay. So James says start with the heat equation, and he's totally right. So this problem specifically is asking us to get the temperature profile. So we want an equation that gives us temperature as a function of R. So that tells us we want to know in detail how does temperature change with space in our solid. And so to do that, we would apply the heat equation. James also started talking about an energy balance where we look at accumulation and in and out terms. The heat equation is based on an energy balance, but we could actually skip that part and just remember that the heat equation is based on a differential energy balance. Yes, Joseph? Okay, so Joseph is asking, could we also use a thermal resistance method here? Could we? So maybe there's a roundabout way of using the thermal resistance method, but keep in mind the thermal resistance method is it's a shortcut. When you use the thermal resistance method, you're basically ignoring what's happening between, so if these are our 2 points, you're sort of ignoring what's happening in between. So you could use thermal resistance method to get the surface temperatures in some way, but to know what's happening inside the solid, the thermal resistance method wouldn't help us all that much. Here we specifically want the temperature profile, which means we want to know details, and we don't want to use a shortcut method that sort of glosses over what's happening in the solid. Does that help, Joseph? Okay, was there another hand out there? Yeah, Blaine? I think you're mixing this up with a different problem, actually. So there's actually no convection happening. I mean, there is convection, but we don't really care about it. We're just given this constant flux. So think of this as like an electric mesh of heating wires that are wrapped around this pipe and providing some sort of constant flux. But then the way you're talking is also very much like the thermal resistance approach, which we don't necessarily want to use here. We're very concerned with what's happening within this solid here, in this cylindrical wall. So we want to solve the heat equation to get the temperature profile. So let's go from there. We need heat equation. So we specifically want to solve the heat equation in one dimension. That dimension is R. So how does temperature vary with R through our system? We're going to be needing certain conditions to actually solve this equation. So what are those conditions called? Great. So we're going to need to know what the boundary conditions are. So we want to solve the equation. So specifically in cylindrical coordinates, this is at steady state. There's no generation. We have constant thermal conductivity. So we could go look up this form of the heat equation. Okay, so does that look familiar to you? And if it doesn't, you could go here. This table in the book is really handy. Okay, so for a cylindrical wall system that's one-dimensional, steady state, and no generation, this is the form of the heat equation. So there's actually a solution to the heat equation giving you the temperature distribution, and you could go here knowing that this is sort of the basic functional form of your temperature distribution. However, these solutions in all three cases are given when your boundary conditions are constant surface temperatures. Those don't happen to match both of our boundary conditions. Yeah, Caleb?
Does stable frequency also assume that the thermal conductivity K doesn't change with R?
Yeah, it does. Okay, you'll just have to remember that. Okay, so this one, yeah, this constant thermal conductivity would also apply here. So this is the form of the equation that we're solving. I'm going to take you through actually integrating the heat equation and applying those specific boundary conditions. So the boundary conditions that we have are, well, why don't you tell me what are our boundary conditions? Great. So at R equals R1, our temperature is just equal to T1. That temperature is just given to us. Great. And then keep going, sorry. I'm trying to get all this on the mic so people watching it later can hear. Okay, so then the other boundary condition, T at R equals R2, T equals T2. So we're actually not given T2. And maybe I should have just left that off the problem. So our other boundary condition is actually going to be this flux condition. So if that were the case and our boundary conditions were just those two temperatures are given, we could just go grab that equation directly. This would just be the solution. It would be as simple as that. But we actually don't know what T2 is. So we have this other flux boundary condition. So we would start solving this problem. 1 over R, d by dr. Okay, so that equals 0. So we would start separating and integrating. Yeah, Donovan?
So how would we write that boundary value for the flux at R2?
Okay, we'll get there. Donovan's asking how would we write the flux boundary condition. So let's just get there. Thanks. That'll be more helpful, I think, in the context of solving the problem. Okay, so we could multiply both sides by R. Get rid of that guy. This just is 0. So then we would separate and integrate. So we would get the derivative of R times dt dr is equal to 0 dr. So then we'd integrate, and we would get R times dt dr is equal to just a constant of integration. The integral of 0 would just be a constant. Okay, so now is a good time. So knowing that we have these different boundary conditions and that one of our boundary conditions is a flux boundary condition, we can now apply one of our boundary conditions. So to Donovan's question, we would have at R equals R2, our flux in the solid. So if we had energy going by conduction this way, we could express that in terms of Fourier's law, and we could equate that flux to what's coming in, and actually we have energy coming this way. So our flux is going to be minus K dt dr at R equals R2, and we're going to equate that to the applied flux that's coming in at our boundary. So our coordinate system has positive R going this way. However, the flux is coming into our system, so that applied flux is going against our coordinate system. So we're going to give that a negative sign. So this is a specific equation that we can use to solve for C1. So by rearranging this equation and putting everything into the right terms, we would actually get, I'm going to skip some steps here. So we'd get C1 is equal to R2 times Q double prime over K. So we were just going to take that and save it for later. So now let's go back to our differential equation here. R dt dr is equal to C1. So now we're going to separate and integrate again. So Donovan, did that answer your question about the boundary condition? Yeah, it did. Okay. So if you take some time and just go back and more closely inspect that term, you can see how using the combination of these two, you can equate C1 to the term here. Okay, so now we go and integrate that. So we get dt is equal to C1 dr over r. If we integrated that, what does this integral look like? What's the functional form? I'm hearing natural log. Good job. So our general form of this equation is tr, t as a function of r, is equal to C1 times the natural log of r plus C2. So we already know what C1 is, so we could just plug in C1 from here. How do we get C2? We're going to apply our other boundary condition. Excellent. So our other boundary condition is now at r equals r1, our t is equal to T1. So that was just given in the problem, that we knew that there was a constant temperature on that inside wall. So applying that to our equation, so now we're just going to substitute these things into that general solution of our equation. Instead of t as a function of r, we're going to use this constant T1 is equal to C1 times the natural log of r1. So we're just substituting this in here and this in here, plus C2. So a quick solve for C2 shows that it's just T1 minus C1 times the natural log of R1. So going back to our general form, we had TR is equal to C1 times the natural log of R plus C2. So now I'm just going to make these substitutions, specifically that C1 is equal to R2 times Q double prime over K, and then C2 is this value. So I'm just going to go make those actual substitutions, and I would get, so now I'm just replacing the constants with the actual values that we solved for. So there's R2 times Q double prime over K times the natural log of R. Now we need to add C2 in there. So C2 is going to be T1 minus C1, and I'll make that substitution for C1 again. So using the properties of natural logs, we could, so this would be a good answer. You might want to simplify it just to make it a little bit cleaner, but we'd get TR is equal to T1 plus R2 times Q double prime over K times the natural log of R over R1. So it has the same basic functional form as that solution that we looked at from the table, but the boundary conditions were given, were different. So our equation ends up looking a little bit different because those constants end up just being a little bit different functionally speaking. Any questions here? So I think the key steps here, so hopefully you've had enough homework problems where this integration process is becoming more natural. If it's not, you should have plenty of problems to practice on and the corresponding solution. So practice walking through how do you integrate these problems, how do you apply the boundary conditions in different circumstances. So I don't want you to get too lost in the math, but I do want you to actually practice the math. The important thing here is you're asked, what is the temperature profile in a solid? And so that should lead you to think, I need to solve the heat equation so I can figure out how temperature changes as a function of my spatial variable. So then the last part B of this problem is just, this is just me being lazy as a grader. And so I want you guys to actually plug in numbers and give me a number. So if you get that exact number, it makes my life a lot easier, and I just give you all the points. If you don't get that exact number, then I go in and try to assess how well you understand the concepts. And I'm pretty generous with partial credit. I really want to see your thought process. So try to be meticulous and thoughtful. Try to keep your equations in algebraic form. And if you mess up on some algebra, let's say you get something really close to this but not quite, you probably just lose 2 or 3 points and get most of the points. So I'm mostly interested in your thought process and specifically, do you understand the concept? Did you have a question?
Yeah. So, you know, when you solve for C1,
Uh-huh.
R2 times the flux over K.
Uh-huh.
So the reason you multiply by R2 is because it's taking place specifically at R2.
Yes. Uh-huh. So the reason that R2 shows up here is because, yeah, at the boundary, this boundary conditions only apply at that specific boundary. So then you start taking variables and plugging in constants, where R would be a variable that could change depending on where you are. R2 is a specific number, yeah. So that's great. So we basically have R2 there equals C1. So this would be R2, so it's specifically that exact value, and then this would also be at R equals R2. So I'd encourage you to go back and look through the solutions, maybe watch this video again, and just try to follow along as best as you can. But really, I want you guys to know what's the concept, what's the thing I'm asking, and then try to find the right solution methodology. So if you went the thermal resistance route, you'd get a lot fewer points on this problem because that is sort of the wrong path from the beginning. So try and make sure you're processing the problem, you understand what the problem is actually asking, and then choose the right solution methodology to get you that particular piece of information you want. So keep in mind the thermal resistance method is a shortcut method. So you could use the thermal resistance in some way to solve for the extreme temperatures, the surface temperatures, but that wouldn't necessarily tell you very much about what's happening within the solid itself. Okay, I think we've got time for one last problem. Okay, well, so we just covered integrating the heat equation. There is definitely going to be one of these on your exam. We talked about cylindrical systems, solving for a temperature profile. There is a differential energy balance happening here, except it happened, that's how we got the heat equation, that's how it was derived. So we didn't really cover that very specifically, but we certainly applied boundary conditions so that we could get our specific form of that temperature profile instead of just the general form. Any other questions? Okay, so here's a different kind of question now, and I apologize that the diagrams, it's hard to distinguish between spheres and cylinders in my very rudimentary graphic design skills. So this is a sphere now. And carefully read these. I even italicized it just so it would be very clear that this is a sphere now. Okay, so a sphere of diameter d equals 1 centimeter generates heat uniformly and is encapsulated by an insulating shell that is 1 centimeter thick. The outer shell does not have a generation term and loses heat to the environment by convection. The process is at steady state, and key properties are found in the diagram below. Okay, so first, part A, we want to find the outer surface temperature of the shell. So, stop and think about what the problem is asking for. So specifically, this problem is asking for one specific temperature. It's not asking for a temperature profile. So that kind of language probably means we don't need to worry about integrating the heat equation in this case. We just want to know the temperature on the outside, T2. Then the second part of this, we want to find the interface temperature, T1. So I'd love to have someone suggest how they would tackle this problem. This one was a homework problem, I think. Yeah, Ivan, we haven't heard from you.
Oh, okay.
So.
So we just have to find my first energy finding the total energy that that's being generated.
Okay.
Generated. Then I would align with the outside temperatures by knowing that that's going to be equal to the convection.
Okay. Okay. So what Ivan is suggesting is an energy balance, right?
Yeah.
So the system is at steady state, right? I hope I told you that. Yeah. The process is at steady state. So we want to know So this is where it gets a little bit tricky, and it takes kind of developing an intuition here. So if we defined this outer section as our system, we could just do an energy balance on the entire sphere. So we would have accumulation, we would have in, out, and generation. So now you got to think about, this is where we've defined our boundaries. So everything that's happening inside of this whole thing would include both this inner sphere and this spherical outer shell. Okay, so what's the accumulation term? 0, because we're at steady state. Great. How is energy getting into our system? Okay, so we could, knowing that something is being generated inside here, that heat's got to get out somehow. So nothing is really coming in. You could think of it differently and have your convection be coming in, and as long as you get the signs right, it should work out the same. But let's assume there's no in. So how is energy getting out? Again, considering that this outer dotted line is the boundary of our system, how is energy getting out of that boundary? By convection. Great. So our out term is going to be H. This is going to be the total surface area of a sphere. That might be a nice thing for your equation sheet. Okay, what goes in the temperature differences here? What's the relevant surface temperature? Okay, great. So T2 is our outer surface temperature. So it's leaving by convection between that outer surface and T infinity. Okay? I'm sorry, I'm trying to save space. I'll move generation. This is really messy. Okay. All right. Is there generation in this system? There is definitely generation in this system, but generation is only happening in that inner sphere. So generation is happening here. So that is uniform volumetric generation, characterized by this Q dot, and the units there can be helpful because it tells us how much heat is being generated per cubic meter. Okay, so just Q dot, are we good? Okay, we need Q dot by the appropriate volume. So that volume is going to be, yeah, this is going to be 4/3 pi R1 squared. This surface area, just to be, this is going to be 4 pi R2 squared. Oh, and this is cubed, my bad. Okay, so now we can compile these different terms of our energy balance. And we would just get Q dot times that inner volume. I'll be consistent here. Times 4/3 pi R1 cubed ends up being equal to H times 4 pi. This is the outer radius now. Okay, so that's our energy balance equation. What do we do with it at this point? Okay, solve for T2. So one equation, one unknown. We just solve for T2. Great. Okay, so that gives us the answer to part A. Just a fairly simple energy balance, but that taking that time, taking a deep breath, and just looking at your system carefully helps you to know, okay, where is it generating, where is it not generating, and make sure you get all the right variables in there. Yeah, Ivan?
So I was just making sure, so there's the reason why we can say that the Q is equal to our convection loss was because steady state, right? So the heat flux is constant throughout the entire thing. Is that what?
The rate of heat, yeah, so basically, let me reword what you were saying. Everything that's generated here, we have some reaction or some electric resistance that's generating heat, and that's got to go somewhere. So all that heat needs to be getting out somehow, and ultimately it's getting out of this outer boundary by convection. That's a really nice segue into part B. So now part B wants us to solve for T1, this other interface temperature. So how would we go about solving for T1 now? So let's change our thought process now, so we can apply a different energy balance at this point. And so now if we apply an energy balance just here around this generating section, and sorry, I'll just do this here so we have the visualization still.
Isn't part B asking for a temperature distribution?
Nope, it's just asking for T1. I don't know if that's too small to read. It says find the interface temperature between the generating sphere and the shell, and then T1 in parentheses. So we just want to find this interface temperature. So now let's do an energy balance just on here. Again, no accumulation, nothing coming in. So if this is our system and we want to know how is heat getting out of there, how is heat getting out? Okay, by conduction, great. So our out term, so by conduction, but it's also got to conduct clear through this whole thick shell. So what's the good shortcut method for figuring out how heat would conduct through an entire solid? Yeah. Okay, so this would be a great place to apply the thermal resistance method. So our out term here could be T1 minus T what? Okay, T2, great. Divided by what? So this would be the conductive thermal resistance between T1 and T2. So that would be looking up what the thermal resistance is for a sphere. Okay, so back to this handy dandy table. For a spherical wall, our thermal resistance looks like that. So this would be our conductive thermal resistance for the sphere. So that would tell us, so when you have heat that has to propagate through a thick solid, and then even maybe through other things, the thermal resistance method can give us a rate equation, which you can use for our in or our out term. Questions there? So we can do this, in this case, because we already solved for, whoa, how did I do that? Okay. We already solved for, man, okay, sorry. Oop. We already solved for T2. So we already know what that is from the previous problem, so we can just look at what's happening between T1 and T2 because we already know what T1 is. Yeah?
Also just use the resistance method when solving for B first and then solving for A, because if you did T1 minus T infinity and then included the resistance of the convection, you could solve for T1.
Yeah, so you could also solve for T1 first. That's excellent. So another way, because the flow of heat, so all the heat is leaving this generation section and it's all getting out somehow. So we could also solve for this, so this rate out here. So our out term, T1 minus T2 over the conductive thermal resistance would also be equal to T1 minus T infinity divided by our total thermal resistance, which is going to be R conv plus R conv. So knowing that when you have two thermal resistances in series, you can just add them up. So these two expressions are equivalent, and this comes back to the idea that when you have heat propagating through multiple media in series, you can take a partial temperature difference divided by a partial thermal resistance, and that would be equivalent to the full temperature difference divided by this full thermal resistance. So there's a couple of different ways of doing that. So either of those would be equally good, and then our generation would be the same as it was before. Q dot times 4/3 pi r1 cubed. So now we're going to get the same situation where we have one equation and one unknown, and now we just solve for T1. What do you mean by the conduction method? Okay. You could use Fourier's law as well. There's going to be there are definitely other ways to solve this, and remember that the thermal resistance method is a shortcut method. So it's also a shortcut method, so you don't have to, you could do Fourier's law and basically integrate that between T1 and T2. That would be equally valid. I think it's just going to be a lot slower and more. So you basically end up solving the heat equation with different boundary conditions. That would also apply, but this would be a good time to use a shortcut method. Yes? Yep. Spherical resistance here, which would be, so this is the spherical. So that would be a spherical resistance. Then the convective is going to be just the same. It's always 1 over HA, except your A changes because now it's a sphere instead of a cylinder or a plane wall.
Will we get this chart on the test, or should we just put it on our sheet?
This chart is already on the test, yeah. You can actually download this whole sheet right now. It's on Canvas.
Okay.
So, and that's pretty much what you'll get on the test.
Okay, thank you.
Uh-huh.
So it's that one? Okay, I was just
Yeah.
going to ask where the equation sheet was. All right.
Yep. On Canvas, I think I have a folder called Old Exams, and it's just in there.
All right, great, thank you.
Uh-huh.